This is Tim Hodges with a quick video on how to use geometric series to represent functions as power series. Okay, let's start off with the formula for the sum of a geometric series. So the sum of a geometric series with initial term A and ratio R is A over 1 minus R. And we know this holds when R has absolute value less than 1. So we can immediately look at the case where A is equal to 1 and R is equal to X, and this will give us the equality that 1 over 1 minus X is 1 plus X squared plus X cubed, the sum of all the powers of X from 0 to infinity. And as we noted above, this will be true when the ratio X has absolute value less than 1. So this gives us a formula for 1 over 1 minus X as a power series, but only for limited values of X. For instance, when X is equal to 2, the left-hand side has a well-defined value of minus 1, but the right-hand side, of course, is just the sum of the powers of 2, which obviously goes to infinity. So the formula doesn't make any sense outside of this range of values of X. We can take different values for the ratio and we'll get a series for similar looking functions. For instance, if we take the ratio to be 2x, then we get that 1 over 1 minus 2x is the sum of 2x to the n, which we can rewrite as the sum of 2 to the n times x to the n, which looks like this. Now this equality will be valid when the absolute value of 2x is less than 1. So that's when X has absolute value less than a half. Let's have a look at a slightly more complicated example, the function 1 over 1 plus x squared. If we write this as 1 over 1 minus negative x squared, then we see that this is the sum of a geometric series with initial term 1 and ratio minus x squared. So it's the sum n equals 0 to infinity minus x squared to the n, which we usually rewrite as minus 1 to the n x to the 2n. So that tells us that we have the equality 1 over 1 plus x squared is equal to the sum of minus 1 to the n x to the 2n. And this is valid when the ratio x squared is less than 1. And in that case, that's again the same as x having absolute value less than 1. We can also vary the initial term and have the initial term a to be a function of x. So the simplest possible example of this would be x over 1 plus x squared. So this is the sum of a geometric series with initial term a and ratio minus x squared. In other words, the sum of x, that's a, times minus x squared to the n. So if we expand this out using basic algebra, that's the sum of x times minus 1 to the n times x to the 2n, and then combining the x to the power 1 and the x to the power 2n, we get the sum n equals 0 to infinity minus 1 to the n x to the 2n plus 1. And this equality is valid when x has absolute value less than 1, just as in the previous case. Finally, let's do another example that just requires a little more tricky algebra, 1 over 5 plus x. So this is not in the form 1 over 1 minus something. So what we should do is first divide the top and the bottom by 5. Now we get 1/5 over 1 plus x to the 5th. So this is the sum of a geometric series with initial term a fifth and ratio minus a fifth. Minus x over 5, sorry. Okay, so that means that it's equal to 1/5 times negative x over 5 to the n, which we can rewrite as minus 1 to the n, x to the n, and now we have a 1/5 times 1 over 5 to the n, so that becomes 1 over 5 to the n plus 1. Now this equality is true when x over 5 is less than 1, which of course is the same as x having absolute value less than 5. So that's just a quick introduction to some very simple ways of expressing functions as power series. There's lots of other familiar functions, and they will require more sophisticated techniques that we will see in later videos.